Okay, so the goal for today is to talk about the acceleration of objects in gravitational fields here on Earth, as well as to describe acceleration versus time graphs. So I'm going to share my screen here. You guys should be able to see the PowerPoint presentation. Now, we all know that anytime you have an object, such as a ball here, and you take that object and you drop it, let's say you drop it from a tall building or from a really high structure, everyone in here knows that that ball is going to fall down and accelerate toward the earth. The reason why it's going to accelerate toward the earth is because there's an invisible force pulling on it, and you guys know what that invisible force is called. We call that force gravity. So gravity acts on the ball and it causes it to accelerate. It turns out, guys, any object that is falling towards the earth has a specific value for the magnitude of its acceleration. Does anyone know what that value is? Anyone just so happen to know? What is the acceleration of gravity here on Earth? Anyone just so happen to know? I know one person knew in my last class. Anybody? Well, scientists have measured the acceleration of gravity to be negative 9.8 meters per second squared. Okay. This is a very, very important number that you guys need to remember because we're going to be using this number a lot in this course. Negative 9.8 meters per second squared is an important constant that will be utilized again and again and again, especially in this unit, especially in the unit after kinematics. That represents the rate of acceleration for any object falling toward the Earth, negative 9.8 meters per second squared, because gravity acts on the object and causes it to accelerate. Since gravity is everywhere, you can imagine why this number is very important in physics, because obviously gravity is an important force. Now, what does this mean? When I say that the acceleration of gravity is a constant value of negative 9.8 meters per second squared, what does that mean? Well, by now you guys should know what a constant acceleration means. A constant acceleration just basically means that an object changes its velocity at a constant rate. So, for instance, in order to make my calculations easy here, so you guys get a sense of what I'm talking about, I'm going to take this number and I'm going to round it off to 10. So rounding 9.8 off to negative 10 meters per second squared. What that means is that if I have a ball and it's falling toward the earth, as this ball falls, okay, after it's in the air for 1 second, the instantaneous velocity of the ball is 10 meters per second at that point. Okay. If it keeps falling after it's in the air for the second second, the instantaneous velocity is 20 meters per second at that point. So the ball keeps falling. After it's in the air for 3 seconds, the instantaneous velocity is 30 meters per second at that point. I think you guys get the point. What is the instantaneous velocity of the ball after the 4th second, assuming it's accelerating downward as it falls from the building? Anyone?
40 meters per second.
Yes, sir. It's 40 meters per second. What is the instantaneous velocity of the ball at 5 seconds?
50 meters per second.
Yes, sir. 50 meters per second. So you guys get the basic idea. Any object that's falling toward the earth accelerates at a constant rate of 10 meters per second per second. Right? That's what this number means. It's just something I need for you guys to know and understand. Okay. So for every second the ball is in the air, notice it increases its velocity by 10 meters per second. Okay. So that is the acceleration of gravity. And guys, the important thing here that I want you guys to know, and again, the real value is negative 9.8 meters per second squared. I just rounded it out to negative 10. But the actual value is 9.8. And of course, the negative just tells me that the ball is accelerating downward, which we call the negative direction. One important thing I need for you guys to know is that this magnitude of acceleration is true for all objects, irrespective of the object's mass. So, guys, it could be an object as small as a golf ball, or it could be an object as large as a piano. It does not matter. All objects falling toward the Earth in a gravitational field accelerate at a rate of 9.8 meters per second squared. Mass does not matter. It accelerates at a rate of negative 9.8 meters per second squared, assuming there's no air resistance. That's an important caveat there. I want to say that this value holds for whenever there's no air resistance involved. And the reason why I want to say that, because some of you guys may be wondering, well, Mr. Taylor, I'm not sure that's right. I'm not sure that all objects accelerate at a constant rate, because if I have a situation here where if I have a sheet of paper and I take the sheet of paper and I drop it, then it appears that the sheet of paper is going to kind of drift down to the bottom before it hits the earth. It doesn't seem as if the paper is accelerating with the same rate as, let's say, a bowling ball or something like that. So if you guys are thinking that, the reality is the reason why the paper may take longer to reach the ground is because there's actually air particles in this room. So as the paper falls down, basically the air particles resist this motion, right? So as it falls, it slams into these air particles, and those air particles basically it resists this motion and causes the paper to slow down. But in the absence of air resistance, assuming I can suck all the air out of this room right now, if I could suck all of the air out of this room right now, this paper will accelerate at a rate of negative 9.8 meters per second squared. If there was no air particles in this room. So that's what this number means. It applies in the absence of air resistance. Okay. Now, let us move on. Now that we have a pretty good idea of what acceleration is, or what the acceleration of gravity is here on Earth, let us transition to acceleration versus time graphs. And again, this is where you guys really need to be sure you're understanding this so that you guys can do your assignment on tonight. Okay, let me... Just a moment, I'm going to share my screen. So guys, before you can do acceleration versus time graphs, it's very important that you guys know how to label your acceleration, or label the correct acceleration on motion maps. So let's do a few examples just to be sure everybody remembers this, because we talked about this before. But I want to be sure everybody is confident in being able to label acceleration on motion maps. Because if you can't do this, then you're not going to be able to do acceleration versus time graphs. Okay, guys, look at this motion map here, this animation of a motion map that I have on the screen. Does anyone in here remember? And okay, does anyone remember for this motion map here, what is the sign of this velocity here and the sign of the acceleration? The sign of the velocity and the sign of the acceleration for this car. Anyone want to tell me?
The velocity is negative.
Uh-huh. What is the acceleration? Positive? Yep, the acceleration is positive. Yes, ma'am. And you knew the velocity was negative because the car is moving in the negative direction, right? It's traveling toward the left. So you knew the car had a negative velocity. But how did you know the acceleration was positive? What is the car doing? It's what? Is it slowing down or speeding up, guys?
Slowing down.
Yeah, it's slowing down. So Guys, since the car is slowing down, remember what we said. Anytime we're slowing down, these two signs are going to be different. It's always the case. The sign of your acceleration will be different from the sign of your velocity anytime you're slowing down. Okay? For objects that are speeding up, the sign of the acceleration matches the sign of the velocity. So everybody got that? Speeding up, same signs. Slowing down, different signs. That's something I need for you guys to remember. Let us look at another situation right here. Again, y'all have to understand how to interpret these motion maps. What is going on here? What is the sign of our velocity and the sign of our acceleration?
Velocity is positive and acceleration is positive.
Yes, sir. You know the velocity is positive because the car is traveling toward the right. Okay. You also know the acceleration is positive because the car is speeding up. So that means whatever this sign is, these signs have to be the same. Because whatever this sign is, this sign has to match it. Because we're speeding up. Whenever you're speeding up, same signs. Slowing down, different signs. Very important that y'all remember that. What about this situation right here? What's going on there?
Positive velocity and zero acceleration.
Yes, sir. It's a positive velocity because we're moving in the positive direction. But notice, guys, the car is neither slowing down nor speeding up. The velocity just stays constant. So the car is just cruising. It's cruising at a constant velocity. As long as the velocity is constant, by definition, there is no acceleration. That's what a constant velocity means. Constant velocity means zero acceleration, no acceleration. If you are moving at a constant velocity, if you're just cruising, you are not accelerating by definition. Okay. Let's do a few more of these motion maps. Again, these motion maps are essential to understanding the graphs. Okay, what's going on here? So guys, is our velocity positive or negative?
Negative.
Yep, because we're moving to the left.
And positive acceleration. Well, yeah. No, negative acceleration.
Negative acceleration, exactly. Yep, it's negative acceleration. And you know it's negative acceleration because the car is speeding up. Since the car is speeding up, these signs have to be the same. These signs have to match. So negative velocity, negative acceleration. And here, so you guys should know that this is a positive velocity because we're moving toward the right. We're moving in the positive direction. What is the acceleration?
Negative.
Negative.
Yep, because we're slowing down. Anytime we're slowing down, these two signs are going to be different. Speeding up, same sign. Speeding up, same signs. Slowing down, different signs. Embed that in your brains. Embed that in your brains. Positive velocity, negative acceleration. And one more motion map. And this right here, this is a negative velocity and zero acceleration. Okay. I mean, is this the one that we did? The one we did before that was at a constant velocity? Was that positive or negative? I don't remember.
Was it a positive
Was
velocity?
okay. I'm just making sure that I hit all the situations. Yeah. So this right here, this is a negative velocity and zero acceleration. We know it's a negative velocity because it's traveling toward the left. We know the acceleration is zero because the velocity is constant. By definition, if you're cruising at a constant velocity, you are not accelerating. No acceleration at all is taking place here. So the acceleration is neither positive nor negative. It's just zero. Now, let us move on to these graphs. Something that a lot of you guys are still struggling with. Okay. So I'm just going to pull up some blank graphs, and then I'm going to share my screen. So I just want to go over various situations with you all. Let me start with this situation right here. If I give you a position versus time graph that looks like this, any and everybody should be able to look at this position versus time graph and tell me immediately which motion map this graph is depicting. You guys should be able to look at this and say, okay, I know what is being depicted there in terms of a qualitative description of motion. Okay. So guys, if you notice, we have a curved line here on a position versus time graph. So clearly we know we have acceleration taking place. It could be acceleration or deceleration, but there's some form of acceleration taking place because we have a curved line. Now, first thing I want to ask you guys, for our position versus time graph, is this showing me an object moving to the left or moving to the right? What do y'all think?
Moving to the right.
No, it's moving to the left. It's moving in the negative direction. Here's how you know that, guys. Look at this curve. Is that curve going uphill or downhill?
Downhill.
Yeah, remember on a position time graph, if the curve appears to be going downhill, that means the velocity is negative. If the curve is going uphill, that means the velocity is positive, meaning it's moving in the positive direction. So in this case right here, our object is moving to the left. In other words, it's moving in the negative direction because we have a line or a curve that appears to be going downhill. Okay. Now, look, the next question is, are we slowing down or speeding up?
We're speeding up.
Speeding up. And the way you know that is because the curve is getting steeper with time, right? So as you read your graph from left to right, I want you guys to notice here the curve it starts off relatively flat, but as time progresses, it gets steeper, right? So it goes from flat to steep, right? Because if you look at this curve here, somewhere around this area, you would see that that's kind of flat. It's pretty much nearly horizontal at that point. But here it gets steeper and steeper and steeper. So remember, guys, as your curve goes from flat to steep, that means your object is speeding up. So speeding up, your curve is getting steeper with time. Slowing down, your curve is getting flatter with time. Something you guys have to remember. Getting flatter with time, speeding up. I'm sorry, getting flatter with time, slowing down. Getting steeper with time, speeding up. Okay. So now, if I had to draw this exact same situation on a velocity versus time graph, in other words, I want to draw an object that's speeding up in the negative direction. Remember, I want to come here to the bottom half, which is the negative end, because these are all my negative velocities. And I want to draw a line that is going further away from zero. Okay. So both these graphs are depicting the exact same scenario. Only difference is one is a position time graph, the other is a velocity time graph. But they both show me an object that is speeding up in the negative direction. And guys, I need for y'all to remember, the reason why I know this is speeding up is because this line here is going further away from zero. Speeding up on a velocity time graph, the line is going further away from zero. If you're slowing down on a velocity versus time graph, the line is going closer to zero. Just like a speedometer, on your speedometer, if you speed up, your speedometer goes further away from zero. If you slow down, your speedometer gets closer to zero. Okay. Now, we just before I get to this acceleration versus time graph here, I want to say this. We just said that this object has a negative velocity, and obviously it has a negative acceleration because it's speeding up. It's speeding up in the negative direction. So guys, that means whenever you're drawing your acceleration versus time graph, you want to always draw, in this case right here, since this is a negative acceleration, you always want to draw your line below the horizontal axis. So, okay, because here we have all negative accelerations. So literally, I'm going to just choose a number, and I'm just going to draw a straight horizontal line through this particular value here, or this value that I chose at random, to indicate that I have a negative acceleration. That's how you do acceleration versus time graphs, guys. Your acceleration time graphs are going to be easy in that they're going to be nice horizontal lines, nice horizontal flat lines. And the reason why they're horizontal is because for this semester, we're going to be dealing with situations where the acceleration will be constant. So the acceleration will be constant. In this case, the acceleration is constant at negative 6.5 meters per second squared. Okay, so for your acceleration versus time graphs, you want to draw nice horizontal lines because, again, in this class, for this semester, we're only going to be dealing with constant accelerations. Now, next semester, when we get to our oscillations unit, we're going to see examples where our acceleration will be changing on an acceleration versus time graph, but that's not until next semester. For now, just know your accelerations will stay constant. Okay. Let us look at another example. Guys, what if I give you a position versus time graph that looks something like this? So what type of motion is this graph depicting?
Slowing down.
It is slowing down, and you know it's slowing down because the curve is getting flatter over time, right? So it starts off steep here, and as time progresses, it flattens out. It's nearly horizontal. So it's slowing down, but it's slowing down in what direction? Positive or negative?
Negative.
Negative, exactly, because the curve appears to be going downhill. So we're slowing down in the negative direction. So if I have to draw this on a velocity versus time graph, do I draw my line on the top half or the bottom half? Guys.
The bottom.
Yep, the bottom, because the velocity is negative. And does my line, does it get further away from zero with time, or does it approach zero with time? What do you think?
Closer.
zero.
Closer to zero, yes. So it's starting off on the negative end, and it gets closer to zero with time. And that's supposed to be a straight line. Let me do that better than that. Okay, so like, wrong color. Hold on, guys. Let me redo this. Okay, so I had something that looks like this. And the velocity versus time graph looks like this. On your velocity versus time graph, guys, be sure your lines are straight sloping lines, no curves on the velocity versus time graph, because that's always true for constant accelerations. Okay, negative velocity, and we're approaching zero, so we're slowing down. So if we're slowing down in the negative direction, what must my acceleration be? Positive, exactly. So now, someone tell me, when I come over here and I draw my acceleration versus time graph, am I going to draw my acceleration line? Am I going to draw it on the top or the bottom?
The top.
Top, right? Because you notice my acceleration is positive. So you just do a straight line like that, straight horizontal line. And of course, there we have a constant positive acceleration. Okay, so that's how you do your acceleration versus time graphs. Remember, for this semester, every situation you're going to be dealing with, the acceleration is going to stay constant. Okay, acceleration won't be changing.
Mr. Taylor.
Yes, sir.
So on each graph, we would start on the specific given point. Like if 4 was the point, we would start on 4 on velocity and acceleration versus time graph.
Right now, I just chose the hypothetical point here. Not hypothetical. I just chose a random point because I'm just giving you guys a generalization of how the trend should look. But just know that if you have a velocity versus time graph here, if you actually take the slope of that line, like if you actually calculated rise over run, whatever you get for your slope is your acceleration. Does that make sense? So let's say my slope here was 9.5. Okay, so if I calculate a slope of positive 9.5 for that slope, then my acceleration versus time graph will literally be drawn at 9.5. Does that make sense?
Yes, sir.
Yeah. So right now I'm just choosing random numbers because I'm just giving you a general gist of how the graph should look. But just know that the value of the acceleration is the value of your slope. Okay, just something to keep in mind. Good question.
Thank you.
Guys, what does this mean right here on the position versus time graph? Notice there's no curves there. There's a straight line on the position versus time graph. So what does that mean?
Constant speed.
Constant speed, exactly. It's constant speed in the positive and negative direction here.
Positive.
Positive, right? Because the line appears to be going uphill. So this is an uphill. So we know we're dealing with a positive velocity. So if we're dealing with a positive velocity and our velocity is constant, that means our acceleration versus time graph needs to be on the top half, and it has to be a straight horizontal line. And again, I just chose a random number just to give you guys a basic idea of how the velocity versus time graph looks like. It's a constant velocity, and it's positive, so it's above the x-axis. And I need for you guys to remember that the slope here, the slope of a position versus time graph is your velocity. So, and we've already talked about this. Whatever magnitude you get for this slope, so in this case, I'm assuming that the magnitude of this slope, if I could actually calculate it, the slope would be 10 meters per second here. So that would be my velocity. Okay. So we know that this is a positive velocity. It's a positive velocity, and the acceleration must be zero acceleration because our velocity is constant. So guess what, guys? That means whenever I draw my acceleration versus time graph, I'm literally going to come right here to the middle point here, zero acceleration, and I am going to draw a straight line through zero to indicate that my acceleration just stays constant. I'm sorry, that my acceleration just stays at zero.
How is it a zero acceleration?
Because the velocity is constant. If you're driving down a highway and you're moving at a constant velocity, are you by definition accelerating? Are you speeding up or slowing down if your velocity is constant?
No.
No. Yeah. So anytime you see a straight line on a position versus time graph here, you know that means a constant velocity. And so we showed that here, constant velocity, which by definition means our acceleration is zero. Acceleration is always zero for a constant velocity. Always. Guys, what's happening here If I give you a position versus time graph that looks like this, what's going on there? What would y'all say is happening there?
It's speeding.
Accelerate
Yeah, accelerating. In what direction?
the positive.
Yep. It's speeding up in the positive direction. You know it's moving in the positive direction because the curve is going uphill. Okay. You know that it's I'm confusing myself. You know it's moving in the positive direction because the curve is going uphill, and you know that it's speeding up because the curve is getting steeper with time. Notice how the curve here starts off pretty flat, and as time progresses, it gets steeper and steeper and steeper. So we're speeding up in the positive direction. So when I draw my velocity time graph, am I going to draw my line at the top or the bottom?
Top.
Top. Is it getting closer to zero, going farther away from zero?
Further away.
Further away.
Yep. So straight sloping line like that. And of course, whatever the slope of that velocity is, that is your acceleration, right? Because, and remember what I said, if we have a positive velocity, and we're speeding up, by definition, our acceleration must also be positive. So the signs have to match. So the acceleration is positive, so I'm going to come over here and I'm going to draw a straight line on the positive end of the acceleration versus time graph. And again, our acceleration will always be constant for this semester. The acceleration is either going to be constant or zero. So all this is saying is that as time progresses, the acceleration stays constant. In other words, the velocity is increasing at a constant rate. What is going on here? What if I give you a position versus time graph that looks something like, hate when I do that. What if I give you a position versus time graph that looks something like this? What's going on there? What type of motion is that object, is that curve depicting?
You're slowing down.
Slowing down in what direction?
The positive.
Yep.
Positive direction.
Exactly. It's moving the positive direction, and you know that because our curve appears to be going uphill. So basically, it's depicting an object that's moving in the positive direction. And notice how the curve is getting flatter with time. It starts off steep, and it gets flatter and flatter and flatter. So remember, on a position versus time graph, if you're getting flatter with time, that means you're slowing down. So we're slowing down in the positive direction. So if I was to come over here to my velocity versus time graph, okay, basically I need to be at the top, but my line has to be approaching zero. Okay. So clearly I have a positive velocity. Guys, what is the sign of my acceleration?
Negative.
Negative, right? Because anytime you're slowing down, these signs are going to be different. So the acceleration here has to be negative. So I'm going to come here. I'm going to draw a straight horizontal line through some random number that I chose, as long as it was negative, to indicate that I have a negative acceleration. And of course, the acceleration is constant because in this class, for this semester, we're dealing with situations where the velocity changes at a constant rate. One more example before I let you guys go. What if I give you a position versus time graph that looks like this? Notice there are no curves there on the position time graph. This is a straight line. So what does that mean for our position versus time graph?
Is it constant?
Constant velocity. Yep. In what direction? Positive or negative?
Negative.
Negative.
Yep, negative, because like the line appears to be going downhill. So that means I'm gonna come over here on my velocity time graph. I'm gonna draw my line below the x-axis or below the horizontal axis, and I'm gonna make sure the line is completely straight and horizontal because there is a constant velocity here. The velocity is not changing as time progresses. In this case right here, the velocity stays constant at 3 meters per second as it's moving in the negative direction. Okay, so we have a negative velocity
And zero acceleration.
and zero acceleration because the velocity is constant, which means my acceleration time graph better be going through zero. Any questions? Okay, guys, this video will be uploaded onto my YouTube page in case you guys want to go back and review some concepts. Stop here. Okay. I see some of you guys were sending me private messages. Guys, I just want y'all to know, if y'all send me a private message, I can't see it while I'm sharing my screen. In fact, the only reason why I can see the chat box is because I actually used one of my other accounts to log into the Zoom call on my other laptop here. So I can look at the chat from here on my other computer. But just know when I'm sharing the screen, I can't see private messages. So as long as I'm sharing my screen, you guys either put a public message in the chat box or just kind of just yell out my name to get my attention. Okay, if there are no questions for me, no immediate questions, you guys are free to go. As soon as I'm done with the Zoom call, I'm going to go ahead and post that assignment in Schoology. If there are no questions, y'all are free to go. Have a good one, everyone.